Chemistry is the study of how atoms and molecules behave, including understanding how atoms and molecules react with each other. In this lesson, we're going to learn how to represent chemical reactions, how to balance them, and how to identify different reaction types. All matter on Earth is made of atoms. However, most substances on Earth are not made out of a single type of atom, but rather groups of atoms bound together. These groupings of atoms are called molecules. This is a ball and stick representation of methane. Methane is made out of one carbon atom bonded to 4 hydrogen atoms. Each individual atom is shown as a sphere, and the bonds between them are shown as the sticks connecting them. Using ball and stick models, we can represent any molecule, even pure atomic substances like oxygen. Here we can see atomic oxygen. Molecular oxygen is 2 oxygen atoms bound together like this. This is the ball and stick model of molecular oxygen. We often represent molecules with text using the molecular formula O2 for oxygen. The molecular formula specifies the number of atoms of each element in one molecule of that substance. So, looking back at molecular oxygen, we see that there is a subscript of 2. This tells us that each molecule of oxygen contains 2 oxygen atoms. Let's look at the model for methane again. Looking at the model for methane, what should the subscript for hydrogen be in the molecular formula? There are some chemicals which are not discrete molecules, where it is impossible to distinguish discrete molecular subunits from others in the chemical. Calcium oxide is an example of this. We can see, looking at calcium oxide, that each calcium atom is bonded to an oxygen which is then bonded to another calcium atom. We cannot specify the molecular structure here, so instead, we specify the empirical formula. The empirical formula is the simplest formula that gives the correct relative numbers of atoms of each kind in a compound. Looking at calcium oxide, we can see that the simplest formula which gives the correct relative numbers of atoms is CaO. For the rest of this lesson, we will represent only the empirical or molecular structure in models or formulas. Now that we know about the different ways we represent models, let's focus on how we represent chemical reactions. We'll represent chemical reactions with both the models as well as the formulas. This is the area where you'll see the models of chemicals in this lesson. Below this area, you'll see the chemical formula. Let's start by looking at the combustion of methane. This is the chemical equation for the reaction of methane with oxygen, which produces carbon dioxide and water. Let's take a look at this equation to understand a bit more about how we structure chemical equations. When representing chemical reactions, we always show the initial chemical species or reagents on the left side of the arrow. The resulting chemical species are called products, and they are represented by the models and symbols on the right side of the equation. Chemical equations show us which reagents react with each other to form specific products. These equations also can tell us how many of each molecule is consumed in the reaction and how many molecules of each product is formed from the reaction. The law of conservation of matter tells us that during a chemical reaction, we cannot create or destroy individual atoms. In other words, we need to have the same number of each atom on each side of the chemical equation. This table is another way we can keep track of how many of each element participates in the reaction. We haven't populated the reaction yet. Let's start by grabbing one molecule of CH4 and dragging it into the reagent side of the play area. Can you see how, when you add a model for methane, the coefficient in front of the CH4 changed to 1? The chemical equation and the models representing each species are linked so that we can more easily keep track of each chemical species. Go ahead and add one of each molecule to the equation. We now have one of each molecule present. Looking at the table, we can see that we do not have equal numbers of each atom on each side of the reaction. In the upcoming section, we're going to learn the process to balance the reaction so that we obey the conservation of matter. We're going to walk through the procedure for balancing chemical equations now. The first step is to set the coefficient for each molecule to 1, and then count how many of each type of atom we have on each side of the reaction. We did this in the last section, so let's see if we're conserving each atom. Looking at the table, we can see that we have one carbon atom on each side of the equation. However, hydrogen and oxygen have different numbers of atoms on each side of the reaction, violating the conservation of matter. In order to fix this, we're going to need to change the ratios of molecules from 1 to new values, which brings us to the second step in our process. Identify the atom which only appears in one species on each side of the periodic table. Which of the atoms listed below is not currently balanced and only appears in one molecule on each side of the chemical equation? Hydrogen and carbon both only appear in one molecule on each side of the reaction, but only hydrogen is unbalanced right now, with 4 atoms on the reagent side and 2 atoms on the product side. Let's go ahead and balance hydrogen by adding another molecule of water to the products. Now, looking at our table keeping track of atoms, we can see that carbon and hydrogen are both balanced, but we have twice as many oxygen atoms on the product side as we have reagents. In this case, all we need to do is add a single oxygen molecule as a reagent to balance the equation. Go ahead and do this. Now we can see that the equation is balanced, with the same number of atoms on both the reagent and product sides of the equation. The study of the relationship between the numbers of reactant and product molecules is called stoichiometry. When the equation is balanced, we refer to it as being stoichiometric. Let's review the concepts behind reading a chemical equation. Which of the following best describes the role of the subscript in the chemical equation? We know a chemical equation is balanced. Hydrogen. Which of the following best describes the role of the subscript in the chemical equation? We know a chemical equation is balanced when So, we've learned how to read a chemical equation and that when we balance a chemical equation, we're changing the ratio of different molecules so that we have the same number of atoms on both sides of the reaction. Now, let's look at a few different types of reactions and practice balancing them. We're going to learn about 4 different types of reactions, how to recognize them, and how to balance them. We'll start with synthesis reactions. A synthesis reaction is any reaction where reagents combine to form a single product. Their structure usually looks like A plus B transforms to C. Let's learn a bit more about these types of reactions by balancing some of them. We'll start with the reaction of sodium with chlorine gas to form sodium chloride or table salt. You can now see the models for each reagent and product as well as their representation in the chemical equation. Right now, the value for each coefficient is 0 because we haven't added any molecules to the equation yet. Recalling the first step in the procedure, let's set the coefficient for each molecule to 1. Instead of doing this by dragging the model over, let's increase the coefficient by clicking the plus icon next to each coefficient directly. Looking at the atom accounting table, we can see that we aren't balanced. We have more chlorine atoms on the reagent side than the product side of the reaction. The next step in our procedure is to identify the atom which only appears in one molecular species on each side and is not yet balanced. In this case, that is chlorine. Go ahead and adjust the coefficient for sodium chloride to balance the number of chloride atoms. Looking at our atom accounting table, we can see that we have unbalanced the number of sodium on each side of the equation. Luckily, sodium is not part of a larger compound, and so this is easy to fix. Go ahead and adjust the coefficient for Na to balance the equation. Great work! We've balanced our first synthesis reaction, and the equation is now stoichiometric. Let's take a look at one more synthesis reaction. Ammonia is formed by combining hydrogen gas and nitrogen gas. This synthesis is called the Haber-Bosch process and is the main way we synthesize ammonia today. Take a look at the equation and see if you can balance it. You can either drag the models over or adjust the coefficients directly. If you need a refresher on the procedure, take a look to your right. Great work! You've balanced 2 synthesis reactions. The characteristic of a synthesis reaction is that multiple reagents are combined into a single product. Now let's take a look at combustion reactions. Combustion reactions are likely the type of reaction you're most familiar with. If you've ever been to a barbecue, you've seen a combustion reaction underway. Combustion reactions occur when a compound reacts with oxygen. Usually this is a carbon-containing compound reacting with oxygen to form carbon dioxide and water, so they have the form in front of you. The easiest way to identify a combustion reaction involving an organic molecule is to look for water and carbon dioxide in the products where one of the reagents is oxygen. This is the reaction that occurs whenever you have burned something. We know the other product of these reactions is heat. We looked at a combustion reaction earlier in the lesson when we talked about methane reacting with oxygen. Now let's look at a combustion reaction involving a slightly larger hydrocarbon, propane. This is the combustion of propane with oxygen to produce carbon dioxide and water, either by dragging models into each side of the equation or by increasing the value of the coefficient. If you need help recalling the procedure, look to your right. Great job! You just balanced the equation for the combustion of propane. You can see that for every molecule of propane, we need 5 molecules of oxygen, which produces 3 molecules of carbon dioxide and 4 molecules of water. Let's look at one more combustion reaction. Methanol reacts with oxygen to form water and carbon dioxide. We know this is a combustion reaction because we have oxygen as a reagent and carbon dioxide and water as products. Go ahead and work through the procedure to balance this reaction. Great job! You just balanced another combustion reaction. Let's learn about another reaction type, displacement reactions. Displacement reactions occur when a more active element displaces a less active element from a compound. You can recognize displacement reactions as they follow the form A plus BC transforms to AC plus B. We also have double displacement reactions, where chemical species swap between multiple compounds. These reactions take the form AB plus CD transforms to AD plus BC and are called double displacement reaction. Let's look at a single displacement reaction first. The reaction of aluminum metal with hydrochloric acid results in the formulation of aluminum chloride and hydrogen gas. The equation is shown in front of you with the models. Please work through the procedure to balance the equation. Great job! You just balanced a single displacement reaction. In this reaction, aluminum replaces hydrogen, forming hydrogen gas and aluminum chloride. Let's take a look at a double displacement reaction. Lead nitrate reacts with potassium iodide in solution to form potassium nitrate and lead iodide. Looking at this reaction, go ahead and try and balance it. Great job! You've now shown you can balance synthesis, combustion, and displacement reactions. Let's look at the final reaction type, decomposition reactions. The last type of reaction we'll learn about are decomposition reactions. These reactions are exactly what they sound like, one substance breaking down into multiple products. They always take the form AB transforms to A plus B. Let's look at the decomposition of calcium carbonate upon heating into calcium oxide and carbon dioxide. The reaction is shown in front of you. Go ahead and balance it. Great job! That was an easy one, but hopefully shows you why we set up the procedure the way that we do. If we start with a coefficient of 1 in front of every molecule, we can count the atoms easily, and sometimes we see that everything is balanced. Let's look at one final example. Potassium chlorate decomposes under heat to potassium chloride and oxygen. Let's balance this final reaction. Great job! You've balanced synthesis, combustion, replacement, and decomposition reactions. Now you know how to make chemical equations stoichiometric, which is the first step to learning how to perform work in the lab. Let's review the different types of reactions. From the options in front of you, select the correct representation of a displacement reaction. From the options in front of you, select the correct representation of a synthesis reaction. From the options in front of you, select the correct representation of a combustion reaction. From the options in front of you, select the correct representation of a decomposition reaction. Great work! You've completed the lesson. If you want to practice any problems, use the table of contents to navigate back through the lesson chapters.